Hello students, this is Indrani ma'am from SIRP Rasayan. In this lecture I am going to explain some important points on benzoin condensation, its mechanism, which type of compound will give this reaction and which will not, and finally some of its application. Let's start. So first we should know what is condensation reaction. We know when two or more identical or different molecules unite together with or without removal of simple molecules like water or ammonia or alcohol ROH or HCl etc. The reaction is called condensation reaction. In benzoin condensation reaction, there is no elimination of small molecules. It is self-condensation reaction of an aromatic aldehyde. Remember, aromatic aldehyde. Specifically catalyzed by cyanide ion. So reaction is taking place in presence of small amount of sodium cyanide or potassium cyanide, and reaction is taking place in ethanol water system. Since cyanide is catalyst, so small amount of sodium cyanide or potassium cyanide is needed. Next point, it is complete reversible process. Product of the reaction is alpha hydroxy ketone. Now benzaldehyde, this is aromatic aldehyde, it gives benzoin condensation, and here by this reaction we will get one alpha hydroxy ketone. With respect to this CO, this carbon is alpha. So here at alpha position OH group is there, so it is alpha hydroxy ketone. It is alpha hydroxy ketone. It is called benzoin. So benzaldehyde by this reaction gives benzoin. Now see here, two molecules of aldehyde are taking part in the reaction, but two molecules of aldehyde react differently. One of them donates the aldehydic hydrogen to the other, because you see in the product here no H is there, aldehydic hydrogen is not there, so it is donating this hydrogen to another aldehyde molecule. It is accepting. See here, this hydrogen is coming here. Aldehyde molecule which is donating its hydrogen, aldehydic hydrogen, it is called donor, and which will accept this hydrogen, it is called acceptor molecule. Now mechanism for benzoin condensation. This is benzaldehyde. This molecule is suppose donor molecule. So oxygen is more electronegative, so this bond will clip in this direction, and this cyanide is nucleophile. So nucleophilic attack of the cyanide ion to the carbonyl carbon atom of the donor molecule is taking place. We are getting this. Now see here, in this species, phenyl group is having minus I effect. Cyanide is electron withdrawing. Therefore, this hydrogen is acidic. So what will happen? Here, migration of aldehydic hydrogen takes place to anionic oxygen atom, and it will form O minus H plus means OH. Here this carbon ion and this species. So this is carbon ion. So this negative charge will be resonance stabilized. It will shift, electron density will be shifted here in this direction, and we will get this. This resonating structure you have to show. This is more contributing resonating structure because here negative charge is on electronegative nitrogen, but here negative charge is on carbon. So this is more contributing structure. Okay. Now what you have to do? From here you have to show once again this resonating structure for the next step, because next step we need this nucleophile, and you know between C minus and N minus, C minus is more nucleophilic. So it will be converted to this resonating structure once again for attack as nucleophile. This is another molecule of aldehyde which is acting as acceptor. Break this bond and show the attack. So this step is now rate determining step. This is slowest step. That's why RDS, rate determining step, I mentioned here. So here what is happening? Nucleophilic attack of this resonance stabilized carbon ion to carbonyl carbon of acceptor molecule is taking place, and we are getting this. So now what will happen? Here acid base reaction will take place. This is base, this is acidic hydrogen. So rapid transfer of H plus from here to here will take place. Then what will happen? You know cyanide is a good leaving group. So rapid loss of cyanide will take place. So we will get here our final product, benzoin. Now why cyanide is very important in this reaction? First of all, you know cyanide is sufficiently nucleophilic, it's very good nucleophile. So here nucleophilic attack takes place easily. Now see here, at this step, cyanide is highly electron withdrawing. This cyanide will withdraw electron density in this direction. pH group is having minus I effect, so it will abstract electron density in this direction. Therefore, this hydrogen is becoming more acidic and reaction is progressing in this direction. And finally, you have seen cyanide is good leaving group. So it is going very smoothly here. We are getting the final product. So three reasons are there to select cyanide here. Cyanide is sufficiently nucleophilic. It's having highly electron withdrawing capability, and it's good leaving group. As we have seen, reaction is unsuccessful with aliphatic aldehydes. Why it is like that? Suppose you are having one aliphatic aldehyde. So you know oxygen is more electronegative than carbon. So electron density will be shifted in this direction. Therefore, this carbon is having partial positive charge and this oxygen is having partial negative charge. And you know alkyl group, if it is aliphatic aldehyde, alkyl group is having plus I effect. So it will decrease the positive charge density here. And we have seen first step is nucleophilic attack of this cyanide ion. So if plus charge density is decreasing here, then possibility of this attack decreases. That's why aliphatic aldehyde will not give this reaction successfully. Another thing, you know HCN is weak acid. Therefore, its conjugate base means by removal of H plus we are getting its conjugate base cyanide, and cyanide is strong base because HCN is weak acid. Therefore, its conjugate base cyanide is strongly basic. So, suppose you are having aliphatic aldehyde with alpha hydrogen. With respect to this CHO, this carbon is alpha, these hydrogens are alpha hydrogens. So in presence of strong base, enolization will take place, and what we will get? We will get enol. Therefore, with this enol, first step will not take place easily. So first point we have seen with aliphatic aldehyde, this carbonyl carbon becomes less electrophilic, so reaction will not take place successfully. And second point we have seen, since this is strong base, therefore enolization of aldehyde is possible if there is alpha hydrogen atom. So here also reaction will not take place successfully. Another thing, in step 2 of the mechanism we have seen that migration of H plus takes place from here to get the carbon ion, and that is possible here if cyanide is there and also if here aromatic ring is there, because this benzene ring is having minus I effect, or you can say whatever carbon ion we are getting after migration of H plus, that is stabilized by resonance from both the side. So this is more stable. So this step will take place smoothly if here aromatic ring is present. So due to these three reasons, reaction is taking place successfully with aromatic aldehyde. Now we will see some more examples. Remember, heterocyclic aldehydes undergo benzoin condensation. So this is furan. If here one CHO group is present, it is called furfural. Remember, furfural undergoes benzoin condensation to form furoin. This is alpha hydroxy ketone. Now see, this is self condensation reaction. If donor and acceptor molecules are different aldehydes, then it is called crossed benzoin condensation. Suppose you are having phthalaldehyde and glyoxal. So here donor and acceptor molecules are different compounds. So here we will get crossed benzoin condensation. So first we will get here two aldehydes, here two aldehydes. So from upper part we will get alpha hydroxy ketone. From lower part also we will get alpha hydroxy ketone. So this is keto form. And by tautomerization, what we will get here? Enol form. So enol form of this is enol. This one. So aromatization is taking place. We will get this enol form. For enol form, what you have to do? For tautomerization, break this bond, shift this electron density here. So here you will get O minus and H plus will come here. So you will get enol. Here also same thing. So this is example of crossed benzoin condensation. Now one important thing, note down, the reaction fails when strongly electron withdrawing group or strongly electron donating group is present at the para position. Now see, this is ortho-nitrobenzaldehyde and this is para-nitrobenzaldehyde. So nitro group is electron withdrawing group. So if this type of group is present at ortho and para position, what will happen? It will give benzoin condensation reaction, but this will not give benzoin condensation. Why? Because at the first step of benzoin condensation we have seen cyanide ion will attack here, we will get this, and then migration of aldehydic hydrogen takes place from here to here, we will get this carbon ion. Here at para position nitro group is there and due to minus M effect of this nitro group, what will happen? It will abstract electron density from this C minus. So here negative charge density will be decreased in such a way that it will not sufficiently nucleophilic to attack to the acceptor molecule. That's where reaction fails here. But here at the ortho position nitro group is there, and at the ortho position steric crowding is there. So due to steric inhibition of resonance, minus I effect is not that much stronger. So here that C minus will be sufficiently nucleophilic and this molecule will act as donor molecule. But here it will not act as donor molecule, so this will not give benzoin condensation, but this will give. This is para-aminobenzaldehyde. It will also not give benzoin condensation because it cannot act as acceptor molecule, because here in aldehyde you know this carbon is having delta plus charge and this oxygen is having delta minus charge. So to act as acceptor, this carbon should be sufficiently electrophilic, but due to plus M effect of this NH2 group at para position, what will happen? It will supply electron density on this carbon, so that positive charge density will be decreased, so it will not act as good acceptor molecule. That carbon center is not sufficiently electrophilic, so this will not give benzoin condensation. But if you are having these two aldehydes, these two will give crossed benzoin condensation, we will get this product. Now which one is acting as donor, which one is acting as acceptor? Benzaldehyde means it can act both as donor and acceptor, as we have seen in the main mechanism. But here dimethyl amino group, which is having plus M effect, it is present at para position with respect to CHO group. So it will act as donor because it cannot act as acceptor molecule due to this plus M effect, because here positive charge density will be decreased, so it is not good acceptor. But due to plus M effect, it will increase negative charge density on the carbon ion which is formed in the donor molecule. So it can act as donor and we will get this. So since it is acting as donor, so here we will get CO, means it will donate H, and this is acceptor, so it will accept that H. We will get this product. In gist, what we have seen for crossed benzoin condensation, donor molecule should have electron donating group at para position, and acceptor molecule should have electron withdrawing group at para position of benzaldehyde. Now we should know what's the application of benzoin condensation. By benzoin condensation we can synthesize benzoin, and benzoin is used to synthesize other compounds. For example, benzoin by nitric acid oxidation will give this compound. This is benzyl. So here what is happening? CHOH is oxidized to CO. By synthesizing benzyl, we can do benzyl benzylic acid rearrangement on it. By reduction with tin HgHCl, we will get pH, CO, CH2pH. So what is happening here? From here reduction is taking place. From this part we will get CH2. This is called deoxybenzoin. Why deoxybenzoin? Because you see here oxygen is removed. That's why deoxy. Now if you do reduction with sodium amalgam, then water. If you are adding water, so what will happen? CO group will be reduced to CHOH. You will get pH, CHOH, CHOH, pH. It is called hydrobenzoin. Similarly, from benzoin, by reduction with zinc amalgam, hydrochloric acid in ethanol solvent, you will get stilbene, pH, CH double bond CH, pH. This is very effective method for the synthesis of stilbene. Here also reduction is taking place. If you reduce benzoin with nickel hydrogen, then you will get pH, CH2, CH2, pH. It is dibenzyl. These all are reduction, this is oxidation. In this video till this, if you like, please subscribe. Thank you for watching.